Thank you for the welcome. This work is a result of a collaboration between the applied research team at Mila and Dialogue, which is a Quebec-based company who provide telemedicine platform. So we observe a growing interest in automatic diagnosis tool and also in telemedicine platform in general to cope with the healthcare shortage, the shortage of labor in the healthcare domain, and also to reduce the workload of a medical practitioner. And then how does automatic diagnostics tool work in general? Essentially, the user, after providing some basic information, will specify a chief complaint. This is basically the reason he's seeking for care. So the AD system, the automatic diagnosis tool, will then ask a question. The patient will answer. Based on that answer, the system will ask a second question, and the user will provide an answer then. So this process will be repeated until either the system thinks it has collected enough information to predict the pathology the patient may be suffering from, or it has reached a maximum number of turns. As we can see, the interaction with the patient is really the crucial part in the whole process, as this is the case with the doctor, with human doctor. The problem is that existing systems are usually designed to identify the pathology the patient may be suffering from using a limited number of turns. Thus, by design, they are prioritizing the accuracy versus the interaction quality. So in this work, we were just interested in a setting where a medical doctor will get involved and review the output of the information collected by the AD system. And in that setting, we believe that the quality of the interaction is as much as important than the accuracy of the system, if not more. So our question is, how do we improve the quality of the interaction? And the answer we provide to that is to get inspiration from medical history taking. Basically, the intuition is that if those systems, while interacting with the patient, could exhibit behavior that is similar to the way doctor will do, then it is likely that the doctor will trust those systems. Having said that, what are the characteristics that we want to get from medical history taken? The first one is differential diagnosis. Basically, when doctors interact with patients, they keep in mind, based on the evidence that they collected, a subset of pathology that is aligned with those evidence. And that differential diagnosis, that subset of pathology, keep evolving as new evidence are collected. So we would like our system to not just predict or identify the pathology the patient is suffering from, but also to recover the full differential diagnosis that the doctor will get. The second aspect that we want to emphasize on comes from the fact that usually the interaction that the doctor carry on with the patient are usually organized in the two phases. At the beginning of the interaction, when the doctor has little information regarding the patient, he tends to ask questions to explore a wide range of diseases. So at some point, when he gets a better understanding of the patient condition, he then asks questions just to make sure that, or to confirm, to validate that understanding. And we want our system also to behave in a similar way. Finally, another aspect that we do care about is how to deal with severe pathology. So when the doctor interacts with the patient and the evidence that he has collected point to a severe pathology, the doctor will likely dig deeper and ask questions that will help in ruling or rule out that pathology from the differential diagnosis. Even if at the beginning, the likelihood of that severe pathology is really small. And we want also the system to focus on those severe pathologies as it is interacting with the patient. So how do we do that? Well, we will use reinforcement learning in this to learn the policy, the interaction policy between our agent and the patient, and also to compute what we call here the differential diagnosis, which is basically a distribution over the set of pathology that we consider. So our agent here has two branches: the classifier network that will be in charge of predicting that distribution over the set of disease that we call the belief, and the policy network that will be in charge in deciding whether or not to continue the interaction with the patient, and if so, what is the question to ask next. As for the state, that will be made of the information, the socio-demographic information related to the user, like the sex, the age, and also all the evidence that has been collected so far. The pathology that we consider to be part of the differential will be the one whose probabilities is higher than a given threshold. And in this case, we set to 0.01 that threshold. For the action, the policy, well, as it is common in reinforcement learning, we will be estimating the Q value of every action giving the state that is provided to the agent. And also, we do not want, let's say, the same action to be repeated during an interaction session, so we will take some precaution regarding that aspect. Now, here is the thing. To induce the desired behavior, what we do is that we introduce 4 auxiliary rewards on top of the environment reward that is common in arrow, namely the exploration reward that will be in charge of evaluating multiple disease at the beginning of the interaction, the confirmation reward that will help emulate the confirmation phase that we discussed earlier, the severity reward that will focus on severe pathology, and the classification reward that will help recover the true differential diagnosis that we do care about. Let's dissect each of these reward components. So for the environmental reward, it's made of an inquiry cost because we don't want the agent to ask unnecessary questions. We have a positive evidence reward, which is like question that will help uncover the symptoms the patient may be experiencing. And what is interesting here is that we don't have a negative reward, negative evidence reward. We don't want to penalize the agent for asking questions about symptoms not experienced by the patient. And the reason is, usually doctor will ask this type of question just to rule out some pathology from their differential. So there's no point in penalizing the agent for asking those questions too. As for the exploration reward, our idea here is to use the junction channel divergence function between consecutive prediction, belief prediction. So our intuition here is to encourage the diversity between those consecutive predictions. And also because This exploration reward is really important only at the beginning of the interaction. We introduce some kind of temporal modulation that will characterize the importance of this component. This is a WX function here in the red over the time. For the confirmation reward, we will use the cross entropy, the usual cross entropy function, and we will try to capture the difference between the cross entropy function while focusing on consecutive belief prediction. The idea here is that by advancing in the interaction, we would like the prediction made by the system to be as close as possible to the ground truth differential diagnosis. And again, here, we do have a temporal modulation that will characterize or capture the importance of that reward component over time. Looking at the severity reward, here, we will consider pathology, severe pathology that are not part of the ground truth differential, but also are not part of the predicted differential. So we want the proportion of those pathology to increase over time. Basically, severe pathology that should not be in the predicted differential, that should be ruled out by the system. The proportion of those pathologies need to increase over time. That is what this function is telling us. And as for the classification, we rely on the cross entropy function as usual, but with a particular focus on severe pathology, again, because what we do care here is that we want severe pathology that are part of the differential to be included in our prediction, to be part of the predicted differential diagnosis. So with all these components, reward component, we train our agent, and then using a version of DQN that is called Rainbow, to learn our policy and infer the differential diagnosis over time. That concludes the design of our solution. Now, to evaluate that solution, we use the DDX Plus dataset, which provide information about disease severity. It does cover 49 diseases and 223 symptoms. It contains questions whose answer could be binary, categorical, or multi-choice. And it has 1.3 million patients. And for each patient, we do have the symptoms that those patients are experiencing, the pathology they are suffering from, and also the differential diagnosis that are associated to their symptom. To compare the solution that we just designed with what have been done so far in the literature, we consider the following baseline. The AARLC solution, which at the time of writing represent the state of the art in reinforcement learning regarding automatic diagnosis system. We also use the diformer, which is based on transformer, and represent the state of the art solution using supervised learning for AD system. We also consider the rule-based solution, BED, that is based on Bayesian belief network. And the underlying idea here is to maximize the utility of a question. So that solution will ask a question only if that question allows maximizing the utility of the evidence that need to be collected. And finally, we use the based system that was originally designed just to collect evidences, but we extended it to so that it could be able to also make disease prediction. So our setup is like we are using 1 million patients for training and 140,000 patients for validation and for tests. We set up the maximum number of turns to 30, and we consider two settings. One setting where we are optimizing each agent to predict the differential diagnosis, and the other one where the agent is trained to predict the ground truth pathology. And each model, including the baseline, has been tuned separately on the validation set. As for the metric, we monitor the interaction length, the positive evidence recall, which tell us what is the percentage of symptoms experienced by the patient that has been recovered or uncovered by the agent. The GTPA, well, that will tell us if the ground truth pathology is part of the predicted differential. And the differential diagnosis F1, that will assess how good is the predicted differential aligned with the ground truth differential. And finally, we do have a metric that assesses how good is the agent in handling the severe pathology. So here are the results that we are obtaining. Overall, all the methods that we explore are good in predicting, including the ground truth pathology in the differential. When they are trained without differential, all the methods have hard time in recovering the real differential diagnosis. This suggests that having differential diagnosis at training is something really important to have. However, when the methods are trained to predict the differential diagnosis, the proposed solution, named CASAN, outperformed the baseline with a margin of 10 points. And regarding the severe pathology, the proposed solution is doing better than the existing baseline by a margin of 4 points. And then regarding the uncover of the symptoms that the patient are experiencing, the proposed solution is also better by margin of 6 points. And all those advantages come at the cost, minor cost, because we observe an increase of the interaction length by, let's say, 1 point if we have to compare to the second, to the diformer one. We wanted with this plot to assess the quality of the interaction. So basically what we are doing here, we are plotting in the exploration confirmation space the trajectory of the interaction for each agent. On the y-axis, we have the exploration score. We try to capture how different is the prediction, are two consecutive predictions made by the agent. And on the x-axis, we have the confirmation score. We try to capture how similar is the predicted differential diagnosis with respect to the ground truth differential diagnosis. And as we can see, the solution that we designed is the only one that exhibits a strong exploratory behavior at the beginning, while slowly going or converging to the ground truth differential. And that is something we do observe, at least from the medical medical history taking. perspective. Here we wanted to analyze the pace at which severe pathology are ruled out or ruled in the differential diagnosis. So the ruling rate here tried to capture over the trajectory out of the severe disease that are in the ground truth differential, how many are in the predicted differential. Similarly, the rule out rate tried to capture out of the disease, the severe one, that are not in the ground truth differential, how many are not in the predicted differential. And we also try to compute the harmonic. It's a kind of F1 score between the two value. And we can see that the proposed solution is the one that exhibits the strongest improvement over the course of the interaction, and it is the one that at the end show the best result. This suggests that indeed the way severe pathology are handled is heavily grounded on the evidence that the agent is collected. And if we focus on the rule out rate, we can observe that at the beginning, the proposed agent is the second worst solution. Like the best one is roughly 20% behind the best one at the beginning, but it is improving over the course of the interaction to be the second best at the end. So what does that mean? It means that at the beginning of the interaction, the proposed system is lenient in including more severe pathology, resulting in false negative somehow. But this is not problematic per se, because remember at the beginning of the interaction, the system knows little about the patient. So it's cautious because with little information is lenient in including more severe pathology under evaluation, and those severe pathology will be ruling out as new evidence will be collected. And that is something we desire for. That is the kind of behavior we wanted our system to have. So that's it. The conclusion of this work is that interacting with patient is not just an automatic diagnosis problem. It's not just a classification problem where we want to identify the pathology the patient is suffering from. Not at all. It is a multi-level classification problem where it is important to predict the differential diagnosis instead of just the pathology the patient is suffering from. And doctors, for those systems to be used by doctor needs to trust the output of this system. And one way to achieve it, at least the perspective that we consider in this work, was to say that if those systems could behave in a way that is similar to the way doctors actually do, then the likelihood for using those systems will be high. Cassandra does improve the evidence collection record by roughly 6 points in absolute, and it's better in identifying the differential diagnosis as well as severe pathology. Again, those results are really promising, but before using this kind of techniques in real world life, there is a need to perform an extensive validation of the agent before deploying it. And also to make sure that you do have data that cover the entire spectrum of pathology you do care about. On the side note, we at Mila, we are hiring, so if you are interested in working in a stimulating environment, do not hesitate. And as an industry, if you're interested in the collaboration with Mila, feel free to reach out. With that, thank you.
Thank you again, Doctor, for your great presentation. Once again, another round of applause for Doctor. And we have mics over there. And I think we only have time for two or three questions. So is there any mic runners other than the one in the middle? Okay. Who has a question?
Hey, thank you for the presentation. I had a quick question about, so you mentioned you had a policy network in your model. I was wondering how you encode the actions in a conversation setting.
The action in the conversation setting. Basically, everything has been encoded, to be honest. It's like you know the type of question you want to add to the system to ask, so you encoded it using a one-dot encoding, whatever you want to use it, but everything has been encoded.
So you have certain types of questions. Those are the actions, right?
Yes, you have the list of questions, but the most important thing is that the list of questions that you have, the questions are related to the symptoms. So basically, when you ask a question, it's because you want to uncover a given symptoms, right? That's it.
Got it. Thank you.
Thank you for the talk. My question is, do you see any performance differences between the deep reinforcement learning approach you mentioned and fine-tuning it, and another thing of fine-tuning a LLM on doctor-patient interactions, which is then prompted to act like a doctor?
Sorry, I didn't get it. Sorry.
So I want to see, do you see any performance differences between the approach you mentioned with deep reinforcement learning and another scenario in which somebody uses a fine-tuned large language model, which is fine-tuned on doctor-patient interactions, that is prompted to act like a doctor?
Yeah, well, the thing with, let's say, patient-doctor interaction, or at least if you rely on the type of data set to train this kind of agent, is that you are just limited to the question the doctor asks, right? You don't have a global overview of what are the symptoms that were experienced by the patient that the doctor didn't ask about. And so your system will be somehow limited in uncovering those symptoms. Maybe that is fine, because if an experienced doctor did ask only those questions, maybe those are the only questions it cared about. But imagine in a setting where a doctor, either senior or junior, will need to review, let's say, the output of this system, and it doesn't know about those symptoms that the system didn't ask about, but the patient was experiencing. I think that will be a kind of limitation of this direction, but it depends.
And thank you. And another question I had is that were there scenarios in which the agent uncovered more information from the patient compared with a doctor, as in the patient is more comfortable talking to the agent, AI in this case?
I think if those systems are not unknowing and they are asking really relevant questions, the user at least will be more confident in providing the answer. It gets unknowing when the question that has been asked is not related to what you really want. And that is where you can lose the user, I would say.
Okay, thank you.